Hey, Thomas, what you doing? We're supposed to be working on our presentation, dude.
Yeah, I know, Malik. I just wanted to beat this one level of this totally not relevant to the subject game.
What game are you playing exactly?
Well, it's called Weapons of Math Construction. It's a first person writing game where the goal is to broaden your math horizons. If I beat the whole game, the god of math will finally come down and tell me what the secret variables that no one but they know are in Dr. Intermont's linear algebra exams. But it's useless in practice and all, but it's a really cool Easter egg that I'd really like to know. But I'm stuck on this one problem.
Well, maybe I can help. What problem you got?
So it's based on an experiment. A research team went to a Lego plant, and when they were there, they looked at three different samples of Lego bricks and examined them against three different qualities, things like structural integrity, temperature when off the assembly line, and so on. It wants me to perform a change of basis on it such that only the most important component is included.
So, can we just do that with our subject today? Like principal component analysis?
Wait a minute, by golly, you're right, we can!
I bet. Let's do it.
Okay, we should probably back up a bit. Principal component analysis, or PCA for short, is a process of reducing the number of dimensions to favor the more significant variables.
We will get into the methodology in a second. But first, we want to go over a couple definitions and equations, some from and some outside the class, that are imperative to calculating PCA.
First, let's refresh everyone on what eigenvectors and eigenvalues are. As our textbook says, a scalar lambda is an eigenvalue of matrix A if there is a non-zero vector x such that ax equals lambda x. This vector x is a eigenvector of A corresponding to its lambda. In PCA, the eigenvectors of each principal component will represent each principal component, and the eigenvalues within the matrix represent the variance of each component.
It's also important to remember what a change of basis is. Our textbook defines this as follows. For basis for vector space V represented by beta and C, a change of basis matrix from beta to C is a square matrix with coordinate vectors of the vectors for beta, but translated by basis C. In PCA, we will perform a change of basis so that our data highlights the more significant components.
There are also a couple definitions from outside of class that we'll be employing while solving PCA problems. First, we're dealing with some averages here, so one key constituent of PCA is a mean-centered data matrix. These subtract the average matrix from a matrix so that the center of distribution of data is at the origin. We'll describe in detail how to arrive at this when we delve into the methodology of PCA.
Finally, another concept necessary for PCA is the covariance matrix. This is a measure between two dimensions which shows how the two variables vary together. The covariance matrix for matrix Z can be calculated by multiplying the transpose matrix Z to matrix Z and multiplying that by a scalar 1 over n, where n is the number of rows in matrix Z.
All right, now let's talk methodology. There are 9 different steps to computing PCA.
First, we want to put our data into a matrix. However, the format of these matrices is different than what we are used to. Instead of the columns representing vectors, the rows of the matrix will instead represent each vector. Let's call this data matrix K, with dimensions n by p.
Second, we're going to calculate the mean for each column. For example, for this example one, the first column's mean would be A11 plus A21 plus A31 all the way up to AN1. And then we divide that sum by 1 over n. We put this into a corresponding 1 by p matrix. This is our mean row vector.
Then, we are going to turn this into an average data matrix by multiplying it to a n by 1 vector, which each value for the vector is 1. Let's call this average data matrix J, and should have the dimensions n by p, just like A. Here's what it would look like.
All right. Since our data now is an average data matrix, or since we now have an average data matrix for our data, we can mean center our data by subtracting j from our initial matrix k. We'll call this matrix B. So in other words, B equals k minus j.
Now that we have recentered our matrix so that the center of this distribution is 0, we can start to look at how variables relate to each other by calculating the covariance matrix of B. Let's call this matrix C. It is important to note that since we are multiplying a p by n matrix by a n by p matrix, we'll end up with a square p by p matrix.
Right. Next, we're going to calculate the eigenvalues and the eigenvectors of C. We've done this in class plenty of times, so hopefully we don't need to walk you through the whole process. But just as a reminder, we can sort these eigenvectors into a matrix P and the corresponding eigenvalues into a diagonal matrix D, such that C equals matrix P times matrix P, the inverse of that. Yeah.
All right, then we reorder the eigenvalues in the diagonal matrix D so that they are in decreasing order. These orders each principal component by significance. Like we said earlier, the eigenvectors represented each principal component and the eigenvalues represent the variance in each component. Don't forget to adjust matrix P accordingly.
Right. Once you've arrived at or arranged your eigenvalues in D and eigenvectors in P as such, we're going to select a subset of eigenvectors from P as our new basis. We can figure out how much each eigenvalue impacts the original data by adding up all of our original eigenvalues and dividing each eigenvalue by that total to get a percent decomposition. For instance, if you wanted to use a number of vectors that represented about 90% of the principal components, you'd add up each of these values in decreasing order until you get a result at or above 0.9.
Let's call the matrix that is made up of the subset of eigenvectors W. Like a P sub beta change of basics matrix, we can use this matrix to project our original matrix onto the eigenvectors. Note that we use our mean-centered data matrix B rather than the original data. Also, since we use row vectors instead of column vectors, instead of multiplying W on the left, we will multiply it on the right.
And there you have it, computing PCA in 9 simple steps. Now let's apply this to my video game so we can get that awesome Easter egg. All right, so.
Interesting. Wait, hold on. Does that say usefulness in column 3?
Hey, don't worry about it. We don't have much time in the game left.
All right. Let's get to work.
Okay, first let's put these in a matrix. It should look pretty much identical to our data, but a bit neater, as the table's already arranged in row vectors.
Now let's find the mean for each column and make that mean into row vector. For example, the first column would be 7 plus 9 plus 5, which equals 21. You can divide that by 3, which is 7. Here's the full 1 by 3 matrix.
As you can see, it reads 7, 8, 4. Next, we are going to make that average data matrix by multiplying that mean row vector by a 3 by 1 matrix with 1s in it, which gives us the following. As you can see now, there's a column of 7s, a column of 8s, and a column of 4s.
All right, great. Now let's subtract the average data matrix from the original matrix to our mean-centered matrix B.
All right, and we end up with 0, 2, negative 2, 1, negative 1, 0, negative 1, negative 2, 3. The next step is to find the covariance matrix by multiplying the transverse of B times B. And here's what that looks like. We end up with 8, negative 2, negative 10, negative 2, 2, 1, negative 10, 1, 14.
Now we have to find our eigenvectors and eigenvalues. Here's our work on how we found the eigenvalues to be 0, 12 minus root 93, and 12 plus root 93. And here's the work we did to find our eigenvectors.
As you can see, here's the first one right here, here's the second one, and here's the third one. All right, now let's rearrange these so that our diagonal matrix is in decreasing order. It would look like this with 12 plus root 93 on the top, then followed by 12 minus root 93, followed by 0.
And here are the corresponding matrix P that we made up of the eigenvalues in the same order. Remember, per our definitions from earlier, we will arrive at C by multiplying P times D times P inverse altogether.
Right. Just because this is a little hard to read, I'm going to translate it. This is negative 2 root 93 plus 2 over 23. This is 3 root 93 minus 26 over 23. This is 1. This is 2 root 93 plus 2 over 23. This is negative 3 root 93 minus 26 over 23. This is 1. And this is 3 halves, 1, 1 as the final one. Luckily for us, the problem told us we only need the largest component for the basis that we're going to project our data on. So we don't need to reason through how many we need to include. But as a reminder, you can once again sum up each of those eigenvalues and then divide by that sum, divide each eigenvalue by that sum in order to determine what percent each component takes up. But in this case, we just need one, the biggest one. So we're going to take that 12 plus root 93 one. Here's what the matrix W, our subset of eigenvectors applicable, looks like. Once again, it's negative 2 root 93, here's the negative right there, plus 2 over 23, 3 root 93 minus 26 over 23, and 1.
So now we apply the change of basis matrix to the data matrix B. Remember, B is on the left side, because we use row vectors instead of column vectors. Here's the end result.
So it looks like our end result is 3 root 93 minus 49 over 23, negative 7 root 93 minus 16 over 23, and 4 root 93 plus 65 over 23. Hey, we did it great!
Wait, hold on. Thomas, hold on, wait a minute.
Hey, what's up?
Can we go back to the covariance step?
Sure, here you go.
Thomas, you forgot to multiply the 1 over n. Now we have to solve the whole problem over again, dude.
Oh man, hey, you're right. It looks like I did forget that. Well, luckily, since it's only a scalar that I forgot, and the eigenvectors are, that means the eigenvectors are only a scalar off from what they should be, which means since that our end result is only another matrix multiplied by that, our scalar is still the same. So we just need to multiply it to our final answer. So we all we have to do is multiply that final matrix by 1 over n, which in this case would be 3. So the matrix would multiply it by 1 over 3. So our real final answer is this: 3 root 93 minus 49 over 69, negative 7 root 93 minus 16 over 69, and 4 root 93 plus 65 over 69.
Beautiful math, beautiful math. So that was a great problem. We just solved a moment ago. But I just realized something really cool. Hear me out.
Yeah, what's up?
What if I told you that principal component analysis has been applied into real-world use?
Well, I mean, duh, look at my video game I was playing a moment ago. I had to examine Lego based on 3 values, and since PCA is all data simplification and analysis, it's safe to assume that it can be applied to almost any subject that utilizes data science. Come on, Malik, this is 5th grade math comprehension.
Oh, all right, Chu, you're thinking ahead of me. All right, I'll give you that one. But what if I told you that you can use PCA for your own personal benefit?
You mean like we just did in the video game?
All right, True. You win. You beat me.
I don't even know what I did. Okay.
You're too smart for me. Well, how about this? Let's take a look at how PCA is used by the intelligent minds of a group of scientists who applied PCA to observe the visual light spectrum from different stars.
Doesn't the color of the star have a positive correlation with its temperature? Like how a red flame is cool, but a blue flame is hot?
Exactly. All right, so before we jump in, let's take a look at the chart of the spectral classification. On our x-axis, we have a letter designated for temperatures of stars, with O being the hottest and M being the coolest. And on the y-axis, we have the star's luminosity with our own star. The sun, our sun, is sitting at a luminosity of 1. Keep in mind that for the x-axis, the temperature rises from right to left. And for the y-axis, the luminosity is on a logarithmic scale. As you can see, the stars on the top left have a higher temperature and luminosity, while the bottom right has a lower temperature and luminosity. So the next question you might have is, why does red signify cooler temperatures while blue signifies hotter? This has to do with the wavelength emission lines of the elements within the star. When a star burns hotter, it is more likely to burn lighter elements like hydrogen and helium, as it doesn't require too much energy to cause fission, thus supporting itself from its own extreme gravitational pull. This inevitably decreases the star's lifespan, as it burns through its supply at a very rapid rate. When hydrogen and helium are at extreme temperatures, they emit light primarily on the shorter wavelength side, so we see more blue than anything. On the other hand, cooler stars are usually smaller in magnitude, so they can create heavier elements like metals without worrying about gravitational collapse, unlike blue stars. These metals, such as titanium oxide, emit red light.
Well, here's a crash course in how wavelength works as well. Let's take a look at the visible spectrum we see right here. As you can see, the spectrum is scaled by wavelength. Wavelengths with a shorter period but higher energy are on the left, whereas wavelengths on the right have a longer period but lower energy. The light we see comes in wavelengths essentially from 400 to 700 nanometers. Light from the color red has a large wavelength, while violet light has a shorter wavelength.
Now that we got through the crash course out of the way, let's take a look at the paper written by several scientists who are trying to find if stars can be categorized based on their spectra, or bands of light rather than their obvious visual color. They took up to 158 spectra and broke them down into expressed wavelengths. Here are 4 stars whose spectra was broken down into a graph for us to visualize. The x-axis is self-explanatory, while the y-axis can be interpreted as like magnitude of expression, where a higher number means a particular wavelength is dominant and more noticeable. Also, note that the scientists use angstroms instead of lambda for wavelength, where we can translate that to as 1 angstrom is equal to 0.1 lambda. The top left shows the spectra of an O star, where shorter wavelengths are more expressed than longer wavelengths, telling us that it is a pretty hot star. The bottom right graph shows the spectra of a K star, where the wavelengths are pretty uniform for the most part, but skew to the longer wavelengths, telling us that it's on the cooler side, a cooler star. The only line to matter at this point is the original line, as we don't know too much about PC lines yet.
All right. The scientists performed a calculation where their matrix presumably consisted of a minimum of 152 rows and columns, while likely using a calculator for assistance, because I can't imagine the pain of doing that by hand. The table here shows us the top 20 eigenvalues found after performing a PCA on that enormous matrix, along with the percentages of the covariance of each set of data. They chose 20 eigenvalues, as any more would have been redundant without yielding results to make sense of. As we can see here, the 20th eigenvalue only makes up 0.0056% of the distribution as a whole. After computing these respective eigenvectors, the scientists then plotted the two values, PC1 and PC2, in a graph to visualize the strong correlation between the two. Which was a seemingly abstract and ridiculously large data set condensed into a pretty simple graph. Similar things can be said for PC1 and PC20 being graphed to the upper right here, and between the principal component with the greatest variance, which is PC1, and the one that was found with the least in the eigenvalues included, which is PC20. Then the bottom two graphs are another way of looking at the data with different PC values. Here it's 5 and 20, and here it's 10 and 20. But are albeit difficult to find trends in the data due to the data points being scattered, having scattered properties. We can look at each and find the origin, and then create standard deviations and make ellipsoids based on that. As you can see, for PC1 and PC2, the ones corresponding to 66.3 and 29.5% of the data, the ellipsoids are much smaller as you go up through standard deviations and than they are with, say, PC5 and PC20, or even PC10 and PC20.
After visualizing the data with the found principal components, the scientists then took the data from PC1 and plotted the data with wavelengths in order to visualize the higher expressive wavelength of each star. The data concentrated on the top left tells us that the stars that dominate at expressing shorter wavelengths, while the bottom right of the slope tells us the stars that dominate at expressing longer wavelengths. More notably, the data of the stars line up in a neat and detailed slope, to which the original data provided was in fact a wide assortment of stars, where the spectra of each star lay in the span of the wavelengths. That is, where the bottom graph comes into play, only to show us that PC20 was essentially the lineup best fit for the initial curve shown above. Looks familiar, huh? The graph of the scientists obtained is identical to the official spectral classification chart. And since the most expressed wavelength correlates to the temperature, we can estimate the average surface temperature of a star.
Wow, I guess PCA really can be used in real life.
All right, so we sure covered a ton in this presentation. Let's review of what we learned.
All right, to calculate PCA, you first have to find the covariance matrix, which once again is 1 over n times the transpose of the matrix times the matrix. And you're doing that on your mean-centered data matrix, which is found once again by subtracting the average matrix from the original data matrix. Once you have that covariance data matrix, you're going to calculate the eigenvalues and eigenvectors of that matrix. Eigenvectors, once again, correspond to the principal components, while the eigenvalues correspond to the variance within each component. Then you're going to choose the eigenvalues with the most significant components to create your change of basis matrix. And then that's finally applied to your mean-centered data matrix, so that we can now see what the data looks like.
PCA has real-life applications and can be applied to virtually any data set to spark correlations among the given original data. Really, it can be used for anything for the most part, ranging from astrophysics, studying space, to something simple as video games.
In fact, literally right before we started filming, I talked with my dad on the phone. And the subject of my classes was brought up, and I was telling him about this presentation. My dad's a gerontologist, or a psychologist focused on aging. He told me that one of his graduate students was actually using PCA on a research paper that they were doing. It really does have applications beyond the scope of even what I knew. Well, Malik, thank you so much for your help today. I guess I should have remembered that the very thing we're studying tied in directly to the problem I had.
Happy to help, my guy. There's just one thing that I'm not too sure of.
What's that?
So, hear me out. I thought you said that the god of math would appear when we solve the problem. So like, where are they?
You know what? You're right. I don't know where they are. But maybe that's the point. Maybe by broadening our horizons in terms of math and using what we've learned in new ways, we've already found them. Not in a literal sense, but a metaphysical.
Understandable. You're right. By learning the material and applying it to the real world, we become the true gods at math.
Not yet. Like in all things, we still got a long way to go. But maybe, just maybe, what what we've learned here today will be the first step to true enlightenment. Thank you.
Thank you.